You've heard it 1,000 times. Two particles, born from the same moment, linked across any distance change one, and the other changes instantly. Spooky action at a distance. Faster than light. Quantum entanglement. And you probably think, deep down, it's like a pair of magical dice, one here, one on the other side of the universe, that somehow always match. A secret signal, an invisible thread, a cosmic connection. That's the story, and it's everywhere. It's also completely, utterly, magnificently wrong. Worse, that wrong idea is hiding one of the most beautiful truths about reality that human beings have ever stumbled upon. And by the end of this, you won't just understand entanglement, you'll see why Richard Feynman said that if you think you understand quantum mechanics, you don't. But we're going to get closer than most ever do. Now, before we dive into this rabbit hole and start pulling apart what you think you know, hit that subscribe button. I'm serious. This is Think Beyond Physics, where we don't just repeat the spooky stories, we tear them down and show you the breathtaking machinery underneath. If you're the kind of person who doesn't want the fairy tale, but the actual, counterintuitive, brain-bending truth, you're in the right place. And trust me, what we're about to uncover changes everything. Because here's the real shocker, that instant change you've heard about? It's not a signal. It's not communication. In fact, according to the rules of the universe, nothing happens at all. When you measure one entangled particle, the other one doesn't do anything. It doesn't twitch, it doesn't receive a message, it doesn't change state. So what in the world is actually going on? To crack this, we have to start by breaking the very picture in your head. The picture of two separate things, communicating. So if it's not a signal, not a thread, not a cosmic phone call, what is it? The problem starts with the language we use. Linked, connected, instantaneous change. These words come from our world, the world of separate objects. A bell rings here, you hear it there. A tug on one end of a rope pulls the other end. We are hardwired to think in terms of things influencing other things across space. And that is the trap. Let me set up the classic scenario, the one everyone gets wrong. Imagine we have two electrons that are entangled. Specifically, their spin is entangled. Don't worry about what spin is right now. Just think of it like a tiny, intrinsic compass needle that, when you measure it, can only point in one of two ways, up or down along whatever direction you choose to check. We take these two entangled electrons and, without looking at them, we send them flying in opposite directions. One goes to a lab in Paris. The other goes to a lab in Tokyo. They are now, let's say, 10,000 kilometers apart. The physicist in Paris decides to measure the spin of her electron along the vertical axis. She gets a result, up. Instantly, she knows that if her colleague in Tokyo measures his electron along that same vertical axis, he will get down. Every single time. The correlation is perfect. Spooky, right? It seems the news of her measurement traveled instantly to Tokyo, forcing the other particle to be the opposite. But here's the first crack in that story, and it's a subtle one that most explanations miss. Let's rewind. What did the physicist in Tokyo actually have in his hand before the measurement in Paris? Did he have an electron with a definite spin pointing down? No. The mathematics and the brutal honesty of every experiment ever done says no. He did not have a particle waiting with a secret answer. He had a ghost, a potential, a superposition of both up and down, tied intrinsically to the ghost in Paris. They are not two separate ghosts. They are one single, non-local mathematical entity. One single thing. This is the critical pivot. You are picturing two dice. The universe is holding one die. A die that just happens to be smeared across 10,000 kilometers. And when you look at one corner of this smeared die in Paris, the entire die, including the corner in Tokyo, snaps into a single, definite face. Not because a message was sent, but because the act of looking defines the property for the whole system. Tokyo's result wasn't caused by Paris, it was revealed simultaneously as part of the same global event. But wait, I can hear your objection. That still sounds like instantaneous something. The revelation in Tokyo happens the moment Paris looks. And you're right to push back. That's where the genius of John Bell comes in, and where our story really begins. Because he asked a question that forced reality to show its cards. Is there any way this could just be a trick? Could these particles have had a secret plan all along, like a pair of gloves, one left, one right, just waiting to be discovered? That seems so much more sensible. So before I reveal why that comforting, hidden variable idea shatters into a million pieces, you need to understand the gamble Bell proposed. A gamble that would pit our cozy, classical intuition against the cold, hard verdict of experiment. Excellent. Let's dive into the history because the story of how we got here is a drama of frustration, accident, and one man's stubborn refusal to let a paradox lie. Our story doesn't start with the spooky stories of the 21st century. It starts with a quiet rebellion in the 1920s and 30s. Quantum mechanics was being built, and it was deeply, profoundly unsettling to its own architects. The math worked with eerie precision, predicting atomic behavior like never before. But the picture it painted of reality made even giants like Einstein nauseous. He famously rejected this idea of spooky action, this notion that a measurement here could instantly define reality over there. He believed in locality, the bedrock principle that nothing, not even information, can travel faster than light. To him, the Paris-Tokyo correlation had to have a simpler, classical explanation. There must be hidden variables unknown, finer details determined when the particles were together, like a pair of gloves. One box gets sent to Paris with a left-hand glove, the other to Tokyo with a right-hand glove. Open a box, you instantly know what's in the other. No spookiness, just ignorance of a pre-existing fact. For decades, this was a philosophical debate. Einstein arguing for a deeper, deterministic reality beneath the quantum weirdness. Niels Bohr, the champion of the Copenhagen interpretation, essentially saying, stop asking for a picture, the math is the reality. And there it sat, a stalemate between two views of the universe. How do you test a philosophy? You can't. Until 1964, in a quiet office at CERN, a physicist named John Stuart Bell, a man not among the original titans but deeply troubled by the same questions, had a monumental insight. He asked, what if Einstein's hidden variables idea, the cozy, glove-like explanation, makes different numerical predictions than standard quantum mechanics? He didn't just philosophize, he forged the debate into a mathematical inequality. A test. Imagine this. Instead of just checking the gloves for left or right, what if you could check them at different angles? Ask the Paris glove not just are you left, but are you left if I tilt my hand 45 degrees? Bell's genius was to imagine measuring the entangled particles along different, randomly chosen axes. If hidden variables were true, if every outcome was a pre-written, local script, then the statistical correlations between these random measurements would have to obey a certain limit. A limit set by common sense. It's a bit like saying if two people are secretly coordinating their stories locally, there's only so much their answers can match if you surprise them with random questions. But quantum mechanics, in its bizarre glory, predicted correlations that would smash through that limit, stronger than any local, pre-planned story could ever allow. This was huge. Bell turned poetry into a blueprint. He provided a recipe for an experiment to ask reality, are you secretly classical, or are you truly, profoundly weird? But here's where history gets interesting. Bell himself thought it was just a theoretical exercise. The technology to perform such an experiment, to create entangled particles, send them apart, make ultrafast, random choices of measurement angles, and compare results, didn't exist. It was science fiction. For nearly a decade, Bell's inequality was a stunning piece of theory, waiting for a world to catch up. Then, in the 1970s and early 80s, pioneers like John Clauser and Alain Aspect began to build that world. Aspect's experiment in Paris in the early 1980s is the stuff of legend. He used clever switches to change the measurement direction while the particles were in flight, so fast that no light-speed signal could possibly coordinate the choice between the two detectors. The universe was given no loophole. The result? The quantum predictions won. Decisively. The Bell inequality was violated. The correlations were stronger than any local, hidden variable theory could ever produce. Think about what just happened. A philosophical preference for a sensible universe was not just disagreed with, it was falsified by a measurement. Reality voted, and it voted for weird. But that's not even the strangest part. The strangest part is what this actually means. It doesn't mean signals go faster than light. It means the question of which one happened first, the measurement in Paris or the collapse in Tokyo, is itself a kind of illusion. In relativity, simultaneity depends on your frame of reference. One observer might see Paris measure first, another, moving at high speed, might see Tokyo measure first. But the correlation holds. The universe refuses to say who caused what. It presents us with a single, unified outcome. Here's where it gets wild. The experiments suggest that the properties we measure aren't just discovered, they are created by the act of measurement itself. And that creation is a global event for an entangled system. It's not a signal propagating through space. It's a fact about the universe resolving itself, all at once. This was the journey from philosophical grumbling to ironclad fact. But we're still left with the burning question, okay, so it's not a signal. What is it really? How can we possibly visualize this? To get there, we have to leave history behind and step into the mind of Richard Feynman, who had a way of cutting through the confusion with a thought experiment so simple, it changes everything. Absolutely. Now we get to the heart of the matter. Forget Paris and Tokyo for a moment. Let's use a thought experiment that Feynman himself loved, one that strips away the distance and gets to the core logical strangeness. Imagine not two particles, but one particle. And not just any particle, but a single electron. You want to measure its position. You set up a detector. But quantum mechanics says something outrageous about this single electron before you measure it. It doesn't have a precise position. It's not somewhere. It's described by a wave function, a cloud of probability smeared out in space. This cloud tells you the odds of finding it here versus there if you look. The moment you click the detector, the cloud collapses. You get a dot on a screen. A definite location. Now, ask yourself, where was the electron right before the click? The brutal, honest answer from quantum mechanics is, it wasn't anywhere. It didn't have a property called position until the measurement interaction forced it to pick one. This is weird enough for one particle. Now, let's entangle two electrons. We're not smearing two separate clouds. We are creating a single probability cloud that describes the pair. This joint cloud isn't defined over locations for particle A and particle B separately. It's defined over pairs of possibilities. It might say, the odds are 50% that you'll find particle A here and particle B over there, and 50% that you'll find particle A there and particle B over here. The crucial, mind-bending point is that this cloud assigns properties to the system, not to the individual parts. The individuals are literally undefined. So when you separate them by a continent, you are not separating two defined things. You are stretching this single, non-local cloud of potentialities. The lab in Paris holds one part of the cloud, the lab in Tokyo holds the other. But it's still one cloud. When Paris makes a measurement, it's not poking one independent piece. It's poking the entire cloud. That poke, that interaction forces the entire cloud of possibilities to condense into one specific, global outcome. Tokyo's piece of the cloud is part of that same condensation event. Let me give you an analogy that works, but only halfway, and its breakdown is where the truth lives. Imagine you have a single $20 bill. You tear it in half. You put one half in an envelope and send it to Paris. The other half goes to Tokyo. The person in Paris opens her envelope. She sees a half of a 20. Instantly, she knows what's in Tokyo, the other half. No signal needed. The correlation was baked in when you tore the bill. This is Einstein's hidden variables. It's the glove story. It feels right. But entanglement is weirder. It's as if you didn't tear a bill. You took a $20 bill and you put it through a magical photocopier that doesn't copy, but entangles. Out come two pieces of paper. But here's the rule. These papers are in a state where they are not half bills. They are potential halves. They are in a superposition of being the left half and right half and being the right half and left half. They are a single financial entity. You send them apart. Now, the person in Paris takes out her paper and performs the ritual of looking to see if it's a left half. At that moment, and only at that moment, her paper becomes a definitive left half. And simultaneously, because it was always one entity, the paper in Tokyo becomes the matching right half. The act of observation in Paris didn't change the Tokyo paper, it defined the property of the whole two-paper system, everywhere at once. This is the core that everyone misses. Entanglement isn't about a relationship between two things. It's a statement that they are not two things. They are one thing. And we, trapped in our classical, local perspective, keep trying to describe it as two things sending messages. The universe isn't doing that. It's just resolving its own unified state. Now here's where your brain might explode. If there's no signal, can we use this to send information faster than light? Let's play it out. You're in Paris. You want to send a 1 or a 0 to Tokyo instantly. You decide that if you want to send a 1, you'll measure your particle's spin along the vertical axis. If you want to send a 0, you'll measure along the horizontal axis. You do your measurement. Instantly, in Tokyo, the state of their particle is correlated with yours. And this is the critical, but the person in Tokyo has no idea what you did. All they see is a random outcome. If they measure along the vertical axis, they'll get up or down at random. If you measured vertically, their result will be perfectly opposite yours. If you measured horizontally, the result will also be random, with a different statistical pattern. But to see that pattern, to tell the difference between your 1 and your 0, the person in Tokyo needs you to send them a second message, by regular old light speed methods, telling them which axis you measured along. Without that classical message, their data is just noise. The correlation is there, but it's useless for communication. The universe built the ultimate secure channel, all the correlation, none of the signaling. It's not a bug, it's a feature of reality. So we have this picture, a single entity, a non-local cloud of potential, collapsing into a global fact. But wait, it gets even weirder. What if we don't measure the same property? What if Paris measures spin up/down, and Tokyo measures left/right? This is where Bell's test lives, and it reveals something even deeper. It reveals that the properties themselves aren't just waiting to be discovered. They are contextual. The answer you get depends on the question you ask. An electron doesn't have a definite spin up/down and a definite spin left/right simultaneously. It has the potential to give you either, but the act of asking one question literally erases the potential answer to the other. And for entangled particles, asking a question in Paris instantly defines which questions in Tokyo will have definite answers. This isn't a flow of stuff. It's a coordination of context. The universe is not a collection of tiny billiard balls with secret numbers written on them. It's a vast, interconnected network of potentialities, where facts only become facts in relation to specific actions, and those facts are inherently global for entangled systems. Stay with me here, because we're about to tie this all together into the big reveal what this tells us about the nature of reality itself. But first, we have to tackle the elephant in the room. What about relativity? If collapse is instantaneous, doesn't that break causality? Here's the beautiful, subtle truth that reconciles it all. This is where the magic of modern physics truly lives, in the reconciliation of two seemingly warring titans, quantum weirdness and relativistic rigor. Because you're right to ask, if something happens everywhere at once, what does at once even mean in Einstein's universe, where simultaneity is relative? The answer doesn't come from choosing sides, it comes from realizing we've been asking the question in a slightly wrong way. Let's construct a relativistic entanglement scenario. Imagine our entangled pair, flying apart. We have two space stations, Station Alpha and Station Beta, moving at a significant fraction of light speed relative to each other. Each has a detector. From the perspective of an observer on Alpha, the detector clicks first, collapsing the wave function, instantly defining the result at the still future Beta. But from the perspective of an observer on Beta, the detector clicks first, collapsing the wave function, instantly defining the result at the still future Alpha. Each frame of reference has its own now. Who caused what? Which measurement was really first? Here's the kicker, both stories are equally valid. And in both stories, the correlations hold perfectly. This isn't a paradox, it's a clue. It tells us that the collapse isn't an event that propagates through spacetime like a ripple. There is no before and after between the measurements that is agreed upon by all observers. Instead, think of it as a single, non-local event in spacetime. A single mark on the fabric of reality that has, by its entangled nature, more than one location in space. When you trace the story backward from the final, agreed-upon data, the list of which detector clicked which way, you find a consistent global story, but you cannot consistently order the sub-events. The universe, in its infinite cleverness, has set this up so that the only thing that's invariant, the only thing all observers agree on, is the final correlation itself. Not the mechanism, not the signal, just the relational fact. Whenever they measured the same axis, their results were opposite. This is profound. It means quantum mechanics and special relativity don't fight over entanglement because there is no transfer of information that could create a causal paradox. Information, the kind you can use to send a message, is strictly local. It's carried by things that move through spacetime on time-like or light-like paths. The correlation forged by entanglement is something else. It's a global constraint, a pre-existing agreement written into the structure of the wave function itself. It's like 2 pages of a single book being sent to opposite sides of the galaxy. Reading page 1 instantly tells you what's on page 2, not because your reading caused page 2 to be written, but because the entire book was authored as one coherent story. The act of reading just reveals the already connected narrative. Now, let's synthesize. Let's bring this all the way back to the hook I started with. What did Feynman reveal about entanglement that everyone gets wrong? He, and the deeper understanding that followed Bell, revealed this: entanglement is not a process that happens between particles. It is a state of being that denies separability, asterisk asterisk. Everyone gets it wrong by visualizing two things and a mysterious link. The truth is, there are no two things. Not in the way we classically mean. There is one quantum state. Period. The spooky action is the shocking realization that our classical intuition of separateness, the idea that objects over there are independent of objects over here, is a useful illusion that breaks down at the fundamental level. The universe is not a collection of distinct, self-contained entities. It is a web of potentialities where here and there can be woven into a single physical fact. This changes everything. It means that at the root of material reality, there is a kind of wholeness, a non-locality that is baked into the mathematics of quantum field theory itself. It's not a bug, it's the central feature. This is why Feynman could be so dismissive of the spooky interpretations. He wasn't dismissing the weirdness, he was dismissing the attempt to force it into a classical, local story. He embraced the math as the true description, however counterintuitive it felt. Shut up and calculate wasn't a dismissal of philosophy, it was an acknowledgement that our words and mental pictures are too small to contain the phenomenon. The map is not the territory. And the territory is wildly, beautifully interconnected in ways that defy our storytelling. So the big reveal isn't a new mechanism. It's a new ontology, a new way of thinking about what exists. What exists are not particles with properties, but quantum fields with excitations that can be entangled across spacetime. Properties like position, spin, momentum are not inherent tags on little balls, they are answers to questions we pose through measurement. And when parts of the field are entangled, the answers we get in one place are fundamentally linked to the questions asked in another, not through influence, but through the intrinsic unity of the field itself. The thing is the field. We are just probing different parts of it. This is the breathtaking truth hidden behind the spooky stories. The universe is not made of tiny, separate building blocks. It is made of a unified, vibrating something, a quantum field, and what we perceive as particles are just localized notes in that symphony, notes that can be harmonized across vast distances into a single chord. That chord is entanglement. You are not looking at a cosmic phone call. You are listening to one single, stretched out note. Now I want to hear from you. What part of this broke your brain the most? Was it the realization that the universe doesn't have a before and after four entangled events that everyone agrees on? Or was it the deeper, more unsettling idea that separateness itself might be an illusion at the quantum level? Drop a comment and let me know what you're still wrapping your head around. I read every single one. This is the kind of conversation that pushes us all to think beyond the textbook. And if this video made you see the universe not as a collection of lonely islands, but as a vast, interconnected ocean of potential, share it with someone. Share it with that friend who loves a good mystery, or the person who still thinks physics is just about balls rolling down ramps. Let's blow some minds together. Because understanding this isn't just about passing a test, it's about glimpsing the true, bizarre, and magnificent fabric of reality. Next time, we're going to take this idea of non-locality and ask an even more dangerous question. If entanglement weaves the universe together, what does that mean for the biggest things of all, for space itself? What if space isn't a fundamental stage, but an emergent illusion, stitched together by quantum threads? Trust me, if you think this was weird, you haven't seen anything yet. That's the beauty of physics. Not comfort, not simplicity. Truth. And truth is always stranger than you think.